word. Oh no. Okay. All right, so I want to just formally write down a couple of things that we did at the end of class last time. So we'll put them in theorem form this time. And what we're building up to, is the idea of what's called the Monodrome Theorem. So essentially, we are going to be working on something that's at the basis of topology of all things. So the question that we're going to be, but not the sort of topology where you're working with sets and product topologies and the sort of nonsense that like goes on in a basic point set topology class. But instead, the question that I want you to keep in mind that we're sort of driving at is, can you use complex analysis to find holes in a domain? Right? So you got some domain, you have some analytic function f defined on it. Suppose I can just like probe the entire domain by starting at a point and drawing paths that go all over the place. If I did that, can I figure out if there's a gap in the domain? So can I find this? And when I say that this is sort of one of the foundational ideas of topology, right? Algebraic topology begins with something called the fundamental group, where what you're doing is probing for holes in a domain by looking to see if I draw a loop inside of it, can I pull that loop back to a point or not without leaving the set, right? So in this case, that loop would not be contractible to a point because I'd have to pass through the hole to do it. Where in this case, if I draw a loop inside, I can contract it to a point because it's very easy. You just pull it back to a point, right? So kind of what we're driving to is one of the places where complex analysis interfaces with this idea. Like, can I say something structural about the domain a function is acting on? Okay, so let's formalize this. This I wrote at the end of last time, and I write a hypothesis this time. So suppose that f and g are analytic on a domain D. Somebody remind me what a domain is? What are the features of a domain? Subset of C. Okay. All right, sweet, man. You got that one. Simply, well, open. Not simply connected, just path connected. It's sort of like, it's basically open and connected, which implies path connected. So open and path connected. Essentially, we think about domains as being things that show up not in two different pieces, but they're sort of like blobs that are in one place. That's the way I think about it. They have to be bounded? No, we spent a whole lot of time in the last couple of weeks talking about unbounded domains, right? It's okay to have f define an unbounded domain. Okay, if let's say let z1 to z2 and so on be a sequence of, and this is an important condition, distinct points in D with zi converging to z in D, and f of zi is equal to g of zi, where I is 1, 2, 3, forever. So I'm just restating a theorem we ended last time with. So we have a sequence of distinct points in the domain. They converge to a point in the domain, and f is equal to g on that sequence. Then f is equal to g on D. We can even use the fancy equal sign. Yep.
Doesn't having a sequence of points in D imply that D is unbounded? Oh, never mind. Wow, okay. No, sorry. Yeah.
Z1, Z2. Yeah, the idea is that there's some limit point here, Z also contained inside the domain. That's the picture. Yeah, so it's a convergent sequence in set. So I think it actually can't be unbounded. Like, so we're not working the extended complex plane now. We're working.
Yeah, gotcha.
Okay. Yep.
Does f and g, like, do we have to assume f and g agree at the limit point, or will we get that?
No, that comes for free actually, because if f and g are analytic, then f and g are continuous, right? And if they're continuous, then if you evaluate, yeah, so the idea here is, this is a good question. So f and g are analytic, but because they're analytic, you get all the other properties that analytic functions have for free, right? Analytic functions are automatically differentiable, and they're also continuous. So f and g are continuous. This is a property that we use all the time. What that means is that it should be the case that f of zi must converge to f of z. Yep.
Why do domains need to be
So you can do weird things with functions if you have a domain like A1 and a domain A2. You can actually do sort of like this sort of thing where you build a function where you use a characteristic function to say something like, oh, f is equal to f1 when restricted to A1, and it's a different analytic function f2 when restricted to A2. So you have a piece that turns on when you're on this domain and a piece that turns on when you're in this. And they could have wildly different behavior on the two pieces. So we want to think, why would I analyze this function on two separate chunks like this when I could just do this piece and say what its properties are, and then think about this as a different function? And then you can put them together, but the theorems are usually true about blob-type domains and not like these weird things where pieces turn on and off. Okay, so why is this true? Why should this theorem be true? So that's not the theorem I actually stated at the end yesterday. The theorem I stated yesterday was the zeros of an analytic function are isolated. Because, yeah, if f and g are analytic, then f minus g is analytic. And f minus g is a function that is 0 for every value of zi. So this is kind of like how these proofs go. You say, oh, well, f and g are analytic, so f minus g is analytic, which means that f minus g of zi is equal to 0 for all I. Continuity would say that it must also be the case that f minus g of z is equal to 0. And f minus g of z must be equal to 0. But that would mean that z was a non-isolated 0 of f minus g. So z is a non-isolated 0 of f minus g. What's the only function that could have non-isolated zeros? It's important here. It's important that this is analytic. And the only analytic function with non-isolated zeros is the zero function. Yep.
What is the z that you're using?
I should be careful here. It's like the limit of the sequence, right? So this is supposed to be the limit of the sequence. So when I say this, I mean the limit of that sequence. So z hat. I'm not trying to confuse with like this. I should have given a special name, right?
Okay.
Yeah. So this z hat, which is the limit of the sequence, must be that word, which is complete gobbledygook, is non-isolated. Z hat would be non-isolated because there would be a sequence of zeros approaching it in an analytic function.
So this, like, we only get that they agree to the extent, like, on the domain that they're both analytic.
It's the domain of mutual analyticity, yeah. And you've got to be a little bit careful here because that means where we're going to go next is we're going to talk about how you could have different branches of the log can agree on one set, and on that set they are the same function. But you can't necessarily start chaining blobs on because they only agree to the extent that they're both analytic if they're analytic on the overlap, then they extend to be analytic on the set that they're mutually analytic on. But you got to be careful when you start chaining stuff together. So you've anticipated one of the things I'm going to say next. Yep.
Is the zero function isolated or analytic because it's just infinite?
It's infinitely differentiable, right? That's it's like the exception basically, right? Like it's the the one function that can be, we talked about having zeros, like being flat locally means you're flat everywhere. Zero function is flat, right? And it's totally happy to be zero everywhere. So I should note here also, the conclusion is thus f minus g is identically 0 on the domain. And that means that f is identically g on d. That symbol is just a fancy symbol that means they are the same function on the domain. I should note that this theorem also actually implies that if you specify that the two functions are equal to any constant, where you specify like any constant value that they happen to be equal on some sequence, then it's going to apply the same thing. Yep.
Could you not, if you were an expert in complex analysis, define an analytic function where there are two simple poles that are within epsilon of each other, for any possible epsilon?
Two simple poles. Well, wouldn't you just have implied then that those are the same simple pole? Because that's the definition of a sequence that's converging, right? If I say that no matter what epsilon you give me, they're within epsilon, then that's foundationally what an analyst would say. They are the same thing. Okay. They're distance 0, right? That's the definition of what it means to be distance 0.
Okay, I guess I'm just trying to be difficult. Can you you can't construct an analytic function with isolated singularity, with non-isolated singularities unless it's the 0 function. But is there a way to like?
Well, isolated zeros, you gotta be careful.
Yeah, sorry.
It's possible to have, so essential singularities can have like sequences of poles approaching them.
Okay.
That can happen.
Okay.
So let's actually connect this up with essential singularities, right? Mm-hmm. So the question you're getting at here is, how can it not be the case that these things can pile in? So remember the trick is, this just says that if they're analytic at the limit, then they have to be the 0 function. If they're not analytic there, you can have sequences of zeros approaching all kinds of nonsense, right? Because you could say, if there's a pole there or an essential singularity at some point, it turns out to be the case that if you have a sequence of zeros approaching some point and the function is not analytic there, the zeros pile up to some limit point, it actually turns out to be the case the function has an essential singularity at that point. Right? So one way to think about that is, if you think about a function where you say, okay, I'm going to have what would it mean to have, say, a sequence? This is actually easier to think about in poles. What would it mean to have a sequence of poles, singularities, that were approaching some limit point? So you have some domain D, and we're going to punch out just single points to say, like, okay, what if there was a pole here, and 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 so on. And these poles ended up approaching that spot right there. So think about this as a sequence of singularities. Now, that's okay, because F's not analytic at any of those points, right? Right. Okay, and let's say that these all approach that point right there, and you want to characterize what that is. Okay. In any neighborhood of this point, there's an infinite number of places where this function blows up, no matter how small you get. Right. So it turns out to be the case that you can't write this. This can't be a pole of the function, because there's no way if you write a Laurent series. When you write a Laurent series down, you're supposed to be able to say, oh, if I factor out k copies of z minus z naught, then I'm multiplied by a function that's never 0 on a punctured neighborhood, right? But there is no punctured neighborhood of this point that's where this function is never equal to 0 or has the pole inside of it. So when zeros and singularities accumulate, they induce essential singularities. Because you can never do that thing where you have a neighborhood where it's like, yeah, take that one point out and everything else is cool. Everything along the way is fine, because you say, oh, well, that neighborhood around that point's a punctured disk and F is totally cool there. Yep.
If you were really in a bad mood, could you construct a function that is infinite poles approaching from one direction and infinite zeros from the other converging to the same place?
Okay. So, that's a good question. Okay, so that's a Mobius transform, right? Okay, so where are the 0 of that function? When we define this, right? This is the basic sort of automorphism of the disk, is what we said these to be. Do you remember where the pole and the 0 are for this function? Where did we say alpha lived? In the disk, right? So alpha is in the disk and alpha bar is not in the disk, right? Okay. So this thing turns out to have this kind of structure. So you have the complex disk, and you have an alpha sitting on the inside, and you have a 1 over alpha bar sitting on the outside. So this is a 0 for that function, and that's a pole for a function. I invite you to think about what would happen. Now, if I take this and I multiply it by another one, it remains an automorphism of the disk, right? So if I took 2 of these and I multiplied them together, if the first one takes the disk to the disk, the second one also takes the disk to the disk. So it's nice. It remains in the same function class. Z minus alpha 1 over 1 minus alpha bar 1 z times z minus alpha 2 over 1 minus alpha 2 bar z. This is called a Blaschke product. So if you start taking these things and you chain them together with multiplication, there are a very well-studied family of functions called the Blaschke products. It turns out you can do this infinitely many times. And if you do, you can just smear zeros all over the inside of the disk, and you can smear singularities all over the outside. And so I invite you to think about what would happen if you started doing this and you chain these things together, and you let this be a sequence that ran out to the boundary, and this then would induce a sequence of poles that was sucking into the boundary from the outside. So yes, if you were in a bad mood, or if you were the sort of complex analyst that liked to study infinite products of automorphisms of the disk, as one does, that would be the sort of thing you might come up with. I think these are called if you actually do this infinitely, I think it's called the Frostman class. So infinite Blaschke products. But you're asking questions that are verging on areas of contemporary, like cutting-edge research and complex analysis. Right? So yeah, these are cool. The pictures of these things, when you start adding more and more things to the side, if you actually track what's happening to the input domain, what the image of the disk looks like under a map where you do like even like a million of these is pretty awful. Uh-huh. Yeah. It's still the disk to the disk. I'm saying if you look at what happens at the boundary, every time you feed the disk into the disk, you're twisting the disk and distorting it. So if you do like a million times, the distortions that you're putting on the disk when you do that, especially if you start like letting these zeros march out towards the boundary, you get some pretty bad geometry on the inside. So yeah, they're all conformally equivalent. Good luck. Yep.
Can you make this product so that eventually the entire complex disk gets zeroed out?
What do you mean?
With each, oh no, we're never mind. If you plug in alpha 1 in that first one, you put alpha to 0, right?
Yeah.
And then you plug in alpha 2.
Oh, you want to fill oh god, that's even worse. You want to actually do some sort of space-filling lattice on the inside of the disk?
Yes.
And okay.
You have to do it on
Yeah, but you could do it on all the rational value points, and then who knows what would come out the other side of that. I mean, it would have to be, what's that? Yeah. Yeah, so,
every point outside of this is
yeah, that would be an awful function. It would be. Yeah, so I guess I use the word automorphism. You have to be careful here, right? Because these things, when you start multiplying them together, you can have things overlap in a way that they still map the disk to the disk, but you don't necessarily get one-to-oneness anymore. It starts wrapping. It could start wrapping it on top of itself, right? I mean, it's like the same thing. Z takes the disk to the disk, and Z takes this to the disk. But if you multiply Z times Z, you end up with a function that wraps the disk over itself once. Yeah, it's conformal locally. It's locally conformal, but it's not invertible. It's not biholomorphic anymore, because you end up with you could possibly end up with an n-to-1 image of the disk sitting on top of itself. Okay. Right, I've got a lot of juice out of talking about isolated singularities there. All right, so what was the second thing I wanted to talk about today? Let's see. Okay. So when do you know that two functions are equal to each other? So if all you need, so what that theorem said was that if f agrees with g, if f equals g on a convergent sequence, So if f agrees with g on a convergent sequence, that's pretty loose condition, and it induces some obvious but important to note like extensions of the theorem. So if f is equal to g on a continuous curve, right? If f is equal to g on a continuous curve, so suppose you have f, which is over here, and then there's some sort of stick, and here's g over here. And let's say that on this interval right here, on that curve, let's suppose f is equal to g on that chunk, then that also must allow you to apply the theorem, because obviously this curve is going to contain a convergent sequence of points that converge to a limit in that same piece. So here, if f and g are analytic on these pieces, and they agree on this curve, then they will agree everywhere on this domain. I should say, we should be careful, I haven't proved that yet. If f and g are both defined on this set, and they agree on a strip like this, then they're equal to each other on the whole set.
They're both defined on the whole set.
Yeah. There's the idea of extending off of this set is going to be actually how we define what it means to be an analytic continuation. So here we're saying f and g are both defined on all of this blob, and we find some strip in the middle where they agree. Because they agree on this continuous strip, they must have a convergent sequence they agree on, which means they must be the same function. The third version of it is the one that we talked about last time, last quarter and a little bit earlier this quarter. If you have f and g defined on something where they agree on an open set. Well, an open set clearly contains a convergent sequence of points that converges to something in the set. So if f and g agree here, if f equals g on an overlap, on an open subset of a domain, then f is identically equal to g on the domain. Yep.
Need the open subset be a domain?
I mean, it needs to be. All you really need to be able to do to assert this theorem is that there's a convergent subsequence. There's a sequence that converges to a point in the same set of analyticity. So here we're saying, oh, f and g are analytic on this blob, and they agree with each other on this piece right here, so they must agree with each other everywhere. So it doesn't have to be an open set inside of it, but if you start intersecting open sets, you end up with an open set.
Sure.
So.
Or I mean that a path connected.
Ah, that's it. Okay. So no, actually. So that, because you could have situations like this.
Yeah.
Right?
But
if f and g agreed on this set, if f and g were defined on this on this sort of set, and they agreed here, well, that's not a domain, but it's still, you can still extract a convergent sequence on which they agree, and so therefore that theorem applies again.
Cool.
Yep.
Is there any, like they agree on a convergent sequence the loosest possible?
I think it's the loosest you can get away with, right? Because it's hard to step back from convergent sequences, because once you get the idea somehow with convergent sequences is that what you're really saying is that there's a set of neighborhoods that collapse where you have some sort of agreement inside the neighborhood, right? And you need some way to induce that sort of marching zero condition in order to make this work. Okay, now the most useful form of this one is we say, oh, f and g are analytic on some domain. This is the most special. This is probably the most commonly used version of this. F and g are analytic on some domain if I can find a single point inside the domain and a single neighborhood around that point on which the functions agree, then they agree everywhere. Right? So if there is a single point in D and a neighborhood, so we'll call that single point, let's call it Z naught, and a neighborhood that looks like 0 is less than 0, let's say Z minus Z naught in absolute value is less than epsilon. That's a neighborhood of that point, right? Little epsilon disk around it. If they agree on this for a single value of epsilon, then the functions are the same function on the domain. Because if you can do this once, then that means that you can keep pulling in and pulling in and pulling in and find that sequence that makes it's the same argument. You can induce the sequence argument, yep.
How do you show them the same on the neighborhood? That's
So, I mean, normally what you do is, in practice is, okay, so how do people do it in real life? They numerically probe up to some amount of error tolerance and then say, look, f and g on this little tiny open set were equal to each other up to 10 to the minus 15. And so therefore, I'm just going to say they're the same function numerically, right? So in practice, in a theoretical sense, I can just say, well, they're equal because I've defined it to be that way, or do some sort of epsilon delta calculation to do it. In real life, when you're doing this numerically, and analytic continuation is intrinsically a numerical thing. People do this all the time in practice. You have a function, and you want to extend its domain numerically. You basically just calculate a bunch of values near some point and say, look, I have two functions, and they were whatever, up to machine precision, they were the same. Well, that's not a proof that they're the same function, but it's the best you can do. So you just assert they're the same function. Because numerical complex analysis is awesome and weird. Yep.
Is there an analog to this in real analysis?
No. Nope. And the reason that there's not an analog to this in real analysis is because there are things. So basically, the extension theorem is what let us take power series and extend them out to all complex numbers, right? But real analysis has some truly atrocious examples of functions living inside of it. So, for example, somebody came to my office and was, I don't remember if it was one of you guys, we were laughing about how absurd some of these real analysis examples are. Like, if you go to Wikipedia, it's very easy to find the page that says a smooth function is not an analytic function. Like, there's a page called a smooth function that is not analytic. So what does smooth mean?
That's a good one.
So smooth is one of these words that's all over the place, right? But in that context, smooth means infinitely differentiable. So it's possible to find an infinitely continuously differentiable function that does not have a power series in real analysis. And the way that you do it, oh yeah, you should be putting your thumbs down for that one. Yeah, this is why real analysis is awful and complex analysis is good. In real analysis, I can say, I'm going to make a function that is 0 over here. It's just 0 and 0 and 0 and 0. I mean, 0 is a pretty smooth function, right? I can differentiate that as many functions. And then once I get to this point right here, I'm going to link it up with something that looks like an exponential function. So I'm just going to say, link it up like this. So here, so you can make this join right here agree. You can make the derivative at this point agree to all orders. So this is continuously infinitely differentiable because the derivative will have this same sort of join between the 0 on the left side and this exponential looking dude on the right side. That will continue to have a very nice smooth connection no matter how many derivatives you take. But if you try to write a power series at 0 for this, half of a power series is not allowed to be the 0 function. So if you did this, you say, oh, this is not analytic at 0. It should be. This is smooth. It's a smooth function, by which I mean infinitely, C infinity, infinitely continuously differentiable at 0. But if you try to write a power series for it down, I'm sorry, we're real analysis. There. The left side of the power series would force that to be the 0 series. It would have to be, because it's identically 0, which means every coefficient would have to be 0. But the right side can't have zeros as coefficients. So this is a function that it fails to be analytic at a point at which it's infinitely differentiable, which is why real analysis is awful. Yep.
The reason it doesn't work in complex is because of the neighborhood.
Because we force it, yeah. Once we extend to the neighborhood thing, it actually snaps off the possibility that this can exist, right? So that's actually part of what motivates the open disk around differentiable points, is that that induces there's something goes really wrong with if you try to extend a function like this, like off of the real line, you get really bad behavior around that link up. Yep. Yeah.
So did Taylor lie to us?
No, he didn't lie. What do you mean?
Taylor's theorem, how would you get a power series with this?
Because this is not complex differentiable at 0.
Well, I meant in real calculus, that Taylor's theorem.
If you go and read the statements of Taylor's theorem in real analysis, you will find that it is very careful to state what they mean about power series.
Hold on.
They are very careful about the hypotheses that they use to make sure that, and you will not see a theorem that says that you get that same relationship of holomorphic and analytic.
I have written them, and maybe my notes were wrong.
Let me, since this is sort of outside the scope,
sure.
we can talk about this. But no, in complex analysis, Taylor's theorem is so what does Taylor's theorem actually prove? With Taylor's theorem, we started with a holomorphic function, and we proved that that function had a power series, right? That's what Taylor's theorem says. If it's holomorphic, that is, if it's infinitely differentiable, then it has a power series, right? So Taylor's theorem is not an if and only if. We think about those theorems as if and only ifs, but things like this, like I said, go to Wikipedia. This is not even the worst of these. You can, you know, how many orders of differentiability do you want? Okay. Okay. Okay, so I guess the upshot here is this theorem, this is the theorem that actually defines analytic continuation. So this is a big dog theorem. So theorem. And I want you to see if you can trace the differences between what we've been saying and what the theorem asserts. So let's let F take A into C, and G take B into C, be analytic on A and B. Okay, so F is analytic on A, G is analytic on B. So now they're analytic on different sets, right? Suppose A intersect B is not the empty set. And F agrees with G, let's say F equals G. F equals G on A intersect B. Now we're going to define a function h. Let h be equal to f of z on A and g of z on B. So h is sort of a piecewise defined function. Then h is analytic on A union B, and h is the only analytic function on A union B that restricts to F on A and G on B. So there's a uniqueness condition here. This means H restricted to the A is F and H restricted to B is G. And that function H, so this is a picture of what we're doing here is this. Now I've got an F that's defined in analytic here, and I have a G that is defined in analytic here. So now these are really different domains of analyticity. The domain of F and the domain of G are different this time. And what we're saying is, if they agree on an overlap, on a non-empty overlap, if they agree on a non-empty overlap, then we can define a new function that is F on this and G on this that is analytic. So we find H on A union B, and that H, H restricted, H is F over here. H is F here, and H is equal to G on this set. And then, of course, in the overlap, it's equal to F and G, because that's where F and G are equal to each other. And the H is unique. There is one function that agrees with F and G. So this is actually a pretty powerful theorem, because it says, if you have a function here, and you have a function here, and they agree just on this piece right here, they're really one function that sort of like takes this function and extends its domain out to here. And this function h that does that, that's defined on both sets, that is what is actually defined to be the analytic continuation. So analytic continuation of F onto this domain B would be h. So h is is called the analytic continuation of F onto the domain B. Or we could call it the analytic continuation of G onto the domain A. So I start with an F that's analytic. I can extend it to another piece as long as I can find a different function that agrees with it on the overlap. So what we're going to see next time is, this is very much a theorem that is true for two sets. As soon as you put a third set into the mix, things start to go wrong. So we're going to talk about like being careful with the natural log and the square root function, and how the idea, I'm going to show you guys exactly how to construct an analytic continuation. So starting here and then moving from disk to disk to disk is one way of actually taking F and saying, I want this domain to be as big as it possibly can be. So the process of finding places where these, where we have two different domains and we have functions that agree on an overlap, that is the art of constructing analytic continuations. Okay, so this will be more clear with examples. I'll see you guys next time. Yep.
Can you change